Next talk is from Andrew Pearcy and Jeffrey Shaw. Both of them, they work at Bloomberg, and Bloomberg is one of our sponsors at the conference. So this is a sponsored talk. And they are going to talk about something that is usually a problem, build times.
Cool. Okay, thank you very much. Can everyone hear me okay? Wonderful. Thank you. I do have some audience participation. We're not all asleep yet. Okay, so as mentioned, I'm Andrew Pearcy, and I've been at Bloomberg for the last 4 years, working in their multi-asset risk systems department. It's a lot of pricing, a lot of C++ infrastructure. I won't go into too much details about the exact finance that we do in that. If you want to ask me about that, you can ask me at the end. But we're here to talk about build times. Just my context, after those 4 years, I've now stepped up to lead a team at Bloomberg. And before that, I had a master's in engineering and mathematics and computer science from Imperial. And if you don't have any questions about C++, at the end, you can ask me about my fun fact, which is that I've cracked on 6 continents. So, cool. Jeff?
Yeah, I've been at Bloomberg for 2 years on the same department and same team as Andrew, actually. Andrew's my TL. And my fun fact is not as cool as Andrew's, but I can quote an embarrassing amount of movies. So if you guys want to talk films, I'm open to that after as well.
Wonderful. Okay, so just a quick outline of what we're going to cover. We're going to go through our motivation. Why do we care about compilation times? We'll have a very brief recap of the C++ compilation model, just that we're all on the same page. I'll then hand it over to Jeff to go through our case study, and that's very much how we identified the bottlenecks in our compilation, the techniques we applied, and then we'll finish with sort of the main takeaways and everything we learned. One thing to get out of the way first. This is not a talk about modules, okay? Yes, modules are coming. Is anyone fully using modules for all of their third-party dependencies? Thought so. This kind of reinforces the talk. So we're not quite ready. We're not there yet. Ideally, a lot of these problems will go away with modules, but this talk is very focused on what can you do in the meantime to mitigate your sort of compilation times until we can actually fully transition to modules. Okay. So motivation, everyone recognize the XKCD comic. We've all had great fun doing our sword fights. But why did we care about this? Well, the first one was just local DevX. When you're developing, if it takes 10, 15, 20 minutes, half an hour to rebuild everything, you lose context. You're going to go away, grab a coffee, you come back, completely forget what you were doing, and you just completely disrupts your flow. The other thing as well is you get what I call refactoring inertia, where if it takes an hour for you to make a change to your code base, and then you need to run it through CI, and then someone needs to approve it, you're not going to bother to do that small change to make the code base better so that you can implement your feature in a slightly easier way. It's just more effort, it slows you down. And so by reducing the compilation times, you get rid of this refactoring inertia. I can just refactor something, make that small change, and make everyone's lives easier. Some other considerations, speeding up CI. So on this, it's very much time to market. How long does it take us to get all the way through the pipeline? Faster pipeline, faster time to market. And potentially in a worst case scenario, if we have a production issue that we need to hotfix, if you're waiting an hour or two just for the CI pipeline to run and your compilation to run and your tests to run, then you could actually get into quite a lot of trouble if you're trying to patch production. So we're all trying to minimize this time frame. One other thing that was specific to us is we wanted to unlock some additional tooling. We had some cases where a few bugs bit us in production, and we wanted to apply static analysis to our code base just to try and catch these bugs earlier. But if our compilation is already taking a long time, applying static analysis, and particularly clang tidy across your code base, makes it even more prohibitively long. So reducing compilation times, reducing static analysis times, everyone wins. That's the idea. And the final one is just resource utilization. We are a big company at Bloomberg. If our code takes a while to compile, then we need more resources. If we can bring that down, then actually free up the resources, free up more machines, less costs. Everyone's happy. My manager's happy. Okay. So that's our motivation. Quick C++ compilation model recap. It's 3 main steps. I'm sure most people in the room know it, but just for completeness, you have the preprocessor, which is your hash includes of all of your headers. You have your macros, you have your ifdefs, a few other preprocessor directives. You then have the compilation phase, where the compiler goes through and parses and tokenizes all of the intermediate files after the preprocessor has run. And then you're doing your template instantiation, and then all of that generates your assembly files, and you get to linking. We're not going to cover linking in too much detail. We're focusing more on the preprocessor and the compilation for this talk. So yeah, that's just covering that. And on the preprocessor side of things, I always like a diagram. So we're going to look at something very, very simple here. I have my header file. I'm going to include string because you almost need string everywhere. I have my class. I'm going to declare that I have this function. And then in my CPP file, I include my header and I include a vector because I might need to use that. And then you actually define what your function is doing. But then once you run the preprocessor, for your very, very simple class, you're pulling in 17,000 lines in the string header, another 13,000 lines in the vector header for your 50 lines of implementation. And so what I'm trying to demonstrate here is that the includes you're pulling in can actually dwarf your source code. So if we can remove any redundant iteration over your includes, then you're bringing down your compilation time. Just the other one, for completeness, a nice little diagram as well. I mentioned that you're running the preprocessor on your CPPs and your headers, and then you get your intermediary files. That's what I showed on the right. And then as the compiler's running over them, you create your object files, you pull in external libraries, link that all together, and you get your executable. So yeah, we're very much focusing on the first two phases here, but that is all for my recap of C++. I'm sure someone could give it better than me, but we're just giving a quick recap. That takes me over to Jeff.
Yeah, so Andrew shared some of the motivations for why we decided to kind of implement the strategies to try to see how we can reduce our compilation times. And the case study that we applied it to was a mono repo with multiple executables, around 1,200 translation units. We're using the CMake meta build system, Ninja build system, and we're compiling with GCC. So yeah, just for you guys to be aware of the resources, and the build time was around an hour. So it was definitely slow, and we wanted to see what we could do to enhance our compilation times. And similar to what the previous talk mentioned, premature optimization is the root of all evil. So we first had to profile, identify issues, see if there are any low-hanging fruit we could address, and yeah, just figure out where the bottlenecks are. And how we did that was through available open source tooling, Clang's ftime trace flag. It actually creates a flame chart JSON file of every translation unit. So this can provide a lot of visibility into headers you may not realize are actually taking a significant amount of time to compile. You can actually use the open trace, or you can open the tracing output with Chrome tracing. And there's another tool, Clang Build Analyzer, which is built on top of Clang ftime trace. It gives you aggregate time trace reports for multiple compilations, and sort of gives you just an output summary, what took the most time, which files are the slowest to parse, what took the longest in the compiler front end, which templates took the longest to instantiate, etc. So we use this to identify certain bottlenecks and then apply the techniques we'll be talking about in this presentation. Here's another chart just to illustrate our build time evolution. We started looking into the case study in December 2022, and as of April, we got that down to around 15 minutes. And after further incremental enhancements, that got down to around 6. What we really want to stress with this diagram is that it wasn't a big bang approach. We slowly just applied a technique, see how much improvement we could get, and slowly just went from there. So we implemented bi-weekly hackathons starting from December, lasting all the way to April. And the further enhancement from 15 to 6 minutes was from the implementation of Unity build, which Andrew will be talking about later on. So yeah, just a quick summary of the techniques we'll be covering. 4 declarations, removing unused includes, which might seem straightforward, but we think it's important. Splitting protocol and implementation, object libraries, precompiled headers, and lastly, Unity build. So 4 declarations and headers. 4 declarations is a strategy where you declare a class type that will be defined later in the scope, and until the definition appears, this class name has an incomplete type, but classes can still refer to each other. So when you have a header that you own, such as a.h, and you include another large header within that, when you have another CPP file, such as b.cpp, that includes a.h, the preprocessor will actually insert the large header contents into the source, as Andrew mentioned in the compilation process. However, if you own large header, you might not need to know about the header contents. You can actually forward declare it, but only if you don't need to know the memory layout, such as the member functions and data members. This technique pretty much allows the compiler to proceed with compilation without needing to know the complete details of the entity being declared. So you minimize dependencies between header files. It allows the compiler to proceed without including the additional header files, and thus leading to a faster compilation. So going into more detail, here's an example. If we forward declare my class and another class is using it, you can actually pass in a pointer, a reference, and a declaration. You can also pass by value and return by value in function declarations. You can do that because at the function declaration, the compiler only needs to know that the class exists to declare the function signature. For member variables, you can declare my class by reference or pointer, but you cannot declare a member variable by value, as that requires knowing the memory layout, as well as any methods, passing by value or calling a method with the forward declared object that will have a compiler error. You can define a function that returns and accepts pointers to the forward declared object, but you cannot pass by value and return by value. That's because the function definition, the compiler needs more information about the class and will throw an error with an incomplete type. And that's because it can't generate the code for the function without knowing the full definition of the class. Some things to note: while forward declaring can be beneficial, we got to avoid excessive forward declarations, as that can just lead to code readability and maintenance issues. It's also bad practice to forward declare what you don't own. And forward declaring types that end up being included in most or a lot of translation units does not actually provide significant benefits for compile times. So yeah, just some things to watch out for and note. And expanding on forward declaring classes, you can and should try to forward declare headers as well. Example is just the iOS forward. This header provides forward declarations for a subset of types defined in the iOS stream header, such as SCD iStream or SCD stream buff. Is really useful when you only need to declare these types without including the entire header. As you can see, iOS forward is much smaller than the full iOS headers. It's around 128 lines versus 26,000. So you should always aim to try to create dedicated headers if you can with forward declared types. And yeah, just the Google style guide, sort of reiterating that you should only forward declare what you own. Now moving on to the next technique or strategy, removing unused includes. Pretty much every header file you bring in when compiling a source file lengthens the time to compile. The bytes have to be read, pre-processed, and parsed. So if you're not actually using a header file, you remove that cost. So tools like include what you use, GraphViz, and Clang Tidy can actually help you identify these transit dependencies, headers within other headers, unused includes, etc. Just to highlight the tool, include what you use, it actually removes these superfluous, sorry, that was a big word. It does this by figuring out what includes are not actually needed for this file and replaces those includes with forward declarations when possible. So it actually helps you perform enhancements. CMake Build API is functionality that uses GraphViz to parse your code and illustrate a dependency chart, similar to the one shown on this slide. And yeah, just to highlight, the more granular an include, the better. So don't be scared to refactor and always examine what you need and what you don't need. The next strategy we'll be talking about is splitting protocol and implementation. Another quote, fundamental theorem of software engineering: we can solve any problem by introducing an extra level of indirection. That's Andrew Koenig. And that's exactly what we're trying to do here. It's often referred to as the impl idiom. It's a design technique that involves separating the interface or protocol of a class from its implementation details. This can be done either through a pointer or through inheritance. Now, the purpose of defining a class in a header file is for the definition to be included in any translation units that include that header file, but that's not always needed. And actually having the implementation details in a header file can have some pain points. It can actually lead to compilation dependencies that are inaccessible to the client code and may not affect the code in any way. Additional header file inclusions may also be required to actually compile the class definition and will increase the size of dependent translation units. And when changes are made to the implementation elements in the header, even without affecting the interface, the code of all dependent translation units will need to be recompiled. So again, it is important to profile and determine where it's actually necessary to implement the strategy. So here we have some sort of interface that we are using, and a lot of files will include that interface. But these files actually only need to know about a few number of methods or functionality from that interface. And when this is the case, you should always consider splitting the implementation from the protocol and basically make the interface as lightweight as possible. So this large header is needed in translator.h due to some implementation details. But because of this, that large header is also included in all the dependent translation units, as I mentioned before. But what we want to do through inheritance or the pimple idiom is remove that large header from the lightweight interface and have it instead point to an implementation base class, whether it's through a pointer or inheritance. This effectively constructs a compilation firewall, preventing the compilation process from being slowed down unnecessarily by expanding headers, and changes to the implementation will not involve recompiling all the translation units that include the interface. So to accomplish this in our own repository, we determined where we needed to implement the strategy through using Clang's ftime trace. We saw that one header, label translator, was being included in many source files, and it was taking a significant amount of time in the compilation process. It also included TCP client, which is a very heavy header. And there are implementation details in this header that require the private member variable pointer, even though most files that included label translator will only utilize the translate function. So instead, we can have label translator act as an abstract base class, and child classes will import those heavy headers if they need to create the definition of whatever function inheriting the abstract base class. So label translator is now acting as a pure interface, and you have another class, which is caching label translator, that will inherit the base class and include the implementation details that requires the TCP client. So we avoid having to define the classes that require the heavyweight headers in the actual label translator file, and stays as a lightweight interface. Keeping in mind what was mentioned earlier, we don't want to forward declare what we don't own, and because we didn't own TCP client, that's one of the reasons why we chose to go with the inheritance strategy. So the header was actually included around 500 times, and the cost of building label translator aggregate build time was 3.77 seconds, and after the enhancements it was 0.03, but the biggest improvement was through the aggregate CPU build time. It went from 1,500 seconds down to around 19.9. These are significant savings, around 1% of the original time. But again, avoiding unnecessary logic in the pre-processing step is just one reason why splitting protocol definitions and implementations can speed up compilation times. Some other benefits I'll just touch on briefly is compilation dependency reduction. You reduce the number of files that need to be recompiled when implementation details change. It hides implementation details, so adding that level of indirection. Build time parallelization, when there's less compilation dependencies, CMake or make can more effectively parallelize the build process. And it also helps you isolate compile time errors. Only the files that include the implementation file will need to be recompiled, making it easier to identify and fix errors. Now the next technique I'll be covering is object libraries. Object libraries can speed up the build process by limiting the number of object files repeatedly generated for the linking step. These libraries are collections of object files that have been compiled from the source files, but have not yet been linked into an executable or another library. So we are basically just specifying what object files we want to be compiled into libraries. It serves as a convenient way to package and redistribute reusable code. In our case, we had around 40 individual test executables, and these executables shared a lot of common code, such as utility functions, test fixtures, or helper classes. So instead of duplicating this common code across multiple test executables, you can actually compile it into an object library and just link it once. It can impact iterative development. For example, each change to the shared code in the object library may require recompilation of all dependent targets, impacting iteration speed. But the object libraries are highly configurable, so it's really dependent on your use case. Now, the last strategy that is pretty important is precompiled headers. Now, most of the time spent parsing code comes from parsing the most commonly used header files. So if you have a header that's reused in multiple different source files, the compiler will precompile, parse, tokenize for every single source file that utilizes it, and this is very wasteful. So the solution is to use precompiled header files. It basically creates a partially processed version of some header files, and then using that version during compilations rather than repeatedly parsing the original headers. So it's built-in functionality in CMake since 3.16. And the concept is to process the work of the headers and translate it into an intermediate representation. And it works really well for headers that are often included but don't change very often, such as standard library headers, the perfect candidate. And this intermediate representation will be prepended to every compiled source file. The time savings can definitely be massive, but it does require some tuning, as they don't actually reduce redundancy in the code generation step. It's just reducing the redundant parsing time. So be aware of what you are including, and over-including can result in diminishing returns. So here's an example using precompiled headers. We've created the foo object library with foo types and foo bars as source files. And we're saying for this object library, we're going to precompile the following headers. That'll generate a CMake PCH file. And this file will actually be prepended to all translation units. So this is why you don't really want to precompile too much. If you have 50 or 60 different headers you try to precompile, then you're actually slowing up the process. For a few headers that are included very often in most translation units, great candidate. That's because when you precompile a header, precompiling the header is actually single-threaded, and compilation of the translation units only starts when the header compilation finishes. But yeah, when you declare a library, you can define the targets, and this file will be generated and included in all your translation unit compilations. So again, it does have a point where there's decreasing marginal returns, but we found a 20% decrease in build time by implementing this technique. So the following strategies and techniques I've mentioned were implemented from December to April, and we saw a reduction of our complete build time from about an hour to 15 minutes. From 15 down to 6, that's where Unity build comes in. That's where Andrew will talk about.
Cool. Thank you, Jeff. So can I have a show of hands? Sorry, show of hands in the room. Who knows what Unity build is? Okay, who's using Unity build? Right. Okay. So the quick idea for those of you who aren't aware is that if you are building a library, you have different CPP files, A, B, and C. All of them are using vector, or all of them have some shared header. And with Unity build, what you're actually just going to do is hash include all of your CPP source files into one, which means that in this case, vector would only be included and passed once. So the idea here is if you include every single source file into one, you don't have any redundant passing. You just go through everything once, and it completely kills out that part of the compiler step. Sorry, that part of redoing anything that you've seen before. This was added in CMake 3.16 as well, the same time that they added precompiled headers. And in theory, all you have to do is just say Unity build mode equals 1 or true, enable it. The default batch size is 8. So what CMake will do is take 8 files, hash include those into one, compile that as like a Unity file, take the next 8, hash include that, and compile. The reason it's at 8 is because if you include everything into one go, you lose your parallelism. So you then become single-threaded. But if you batch it into reasonable sizes, I'm assuming 8 is a reasonable size by their definition, then you still get the parallelism, but you get the benefit of you only have to pass some of those headers 1/8 of the time. So this is what CMake is doing under the hood. When you tell it just to create a Unity build or enable Unity builds, it's creating those Unity files for you. It hides them away in the build directory, hash includes everything, and processes them. But the issue is, in theory, you just enable it and it works. I was going to ask if anyone in the room had tried to transition to a Unity build. Yes, some people have. Was that a question? Okay. Okay. This is what we went, and I was hoping you just enable it and you're done, but it wasn't that easy. So this is why after a few months we gave this a go and tried to resolve everything. Now the first issue when you try to enable Unity build is you will almost certainly get a compilation error. The first one that we ran into was just anonymous namespaces. If you have an anonymous namespace, you get static linkage in your translation unit. It's great. I don't want to show the rest of my files that I have this function. So if I have a print function in a.cpp and a print function in b.cpp, they can live perfectly happily in isolation. But as soon as you hash include them, you get a compiler error. And so what's the solution here? Well, there's a few options. You can rename all of your clashing functions. I'm sure everyone would like to do that. That is one option. You can manipulate your namespaces to try and get them referencing the file that they're inside. If you want to go through and change all of that, that's one option. But CMake, when they added Unity support, actually thought of this and introduced the idea of a Unity ID. So you can set up in CMake a Unity ID. That will then, the one change you do have to make is use Unity ID when you declare your anonymous namespaces. We did experiment with using Clang Query and Fixits to try and do this and had moderate success. But worst case scenario, you can do a find and replace with some caveats. But what this actually does is it gets expanded to a unique ID, which CMake does for you. And hey presto, your anonymous namespaces are now anonymous again. How it actually does this is in your CMake lists, you just set the target properties, you give it your unique key. So in our case, Unity ID is our unique string. That's what we're going to use everywhere. And then when it's hash including all of your CPP files, it's undefining and defining a unique entry, okay? Restoring your anonymous namespaces for you. That solved our first problem. Next up was template instantiations. So if you have a header, we're going to have some templated function that does something generic on a vector of any type. And then in our CPP file, we're going to use that template to do something generic on, say, a double. And then in another CPP file, we happen to include a.h because we might want that template for some cases, but we're also going to have a specialization. And now, when it comes to Unity build, if a.cpp gets included before b.cpp, you get a compilation failure because you instantiate the template when you use it, but then you try to specialize it after you've instantiated it. So now our compilation is dependent upon the order of our files. And that's not really ideal. There's a few solutions to this, which I'll come on to later. But the next one is template overloading. And this is the one that I'd actually encourage you, if you are falling asleep, to pay attention to. Because what we had is one file where we had a print function. We were trying to stream out these dates to do some sort of auditing logic. So we had, okay, this is what happened. This is what you changed. You changed these dates. And then in another file, there was also a templated print that would take a vector of anything. And what we discovered is that our tests started failing because you pick up the explicit definition that's a better match than the template. And so this might be a trivial example for printing, and I think we are slightly lucky in the sense that our tests caught it. Shout out to having good test coverage. But if you don't, you are changing the underlying implementation of your code, and your compiler won't tell you. So you can swap in an implementation and be none the wiser. So this is the one caveat that we ran into with Unity build, which is actually a little bit scary. If anyone has a solution to this at the end, I'm all ears. The final one we ran into, which I was tearing my hair out for at least half a day, is we had a third-party library. It had some component with an enum, and there was a widget. And when we tried to do our Unity build, we included a load of our third-party libraries together, and I got a compilation error. Expected identifier before numeric constant. Anyone have any ideas? Okay, yeah, fair enough. Last time I did this, they didn't shout out the answer. But yeah, but I looked at this, I was like, okay, am I redeclaring widget somewhere? Is there another enum that's clashing? And I finally broke down and ran the preprocessor, and hey presto, 7 equals 2. Fair enough, I can understand why you won't compile. And as shouted out, in one of our other third-party libraries, there was a macro. And so now you have the issue of macros interfering when you're including all of your files together. Now, if anyone's ever tried to go to a third-party library and say, hey, can you change this macro? I feel like you might not have much luck. So how do you get around this? Again, looking at the CMake implementation, you have the option to skip Unity build inclusion. So if you just have an individual file that you know cannot be compiled in combination with all of your other files, you can just assess and say, hey, I'm going to compile this individually on its own, and it goes back to the old behavior that you would have had. The other option you have is manually grouping files together via the Unity group. So we actually ended up doing this with our third-party libraries. In the macro case, we're like, hey, all of these files depend on this third-party library. All of these files depend on this third-party library. We'll try and compile them separately because we know there should be some shared dependencies here. So you should get some benefits, but there's no need to actually compile them together. So how did we do? We spoiled it a little bit with the graph, but when we started with the regular build, we're at 15 minutes for 1,200 targets. With the Unity build, default batch size of 8, so groups of 8 files together, that got us down to 9 minutes. And then just setting infinite, so for every library that we had, throw everything into one file, that got us down to 6 minutes. But the other thing that we were slightly impressed by is that static analysis. I mentioned right back at the beginning that we were trying to unlock Clang Tidy for our code base. With our 15-minute build time, we'd got to 40 minutes of static analysis, which was acceptable, but not ideal. And so once we enabled Unity builds, we got that down to 4 minutes. And thinking about this, we have 55% reduction in build time, but that's also including the linking time. But for the static analysis, you're getting 90%. And roughly speaking, it makes sense to me if anyone, again, knows any more about this, I'm all ears. But you have 10 times fewer compilation targets. You're having to pass all of your dependencies 10 times fewer for the static analysis side of things. So it generally makes sense to me, but I haven't quite gotten to the bottom of that, if that is exactly the reason why this is happening. So that's Unity build. Potential drawbacks. So you might get some issues from incremental builds, because now, previously if you were compiling one translation unit, you change that one translation unit, that's all you have to recompile. With Unity build, you have to compile a much larger translation unit because you have all of these 8 files compiled together. So you might get some drawbacks on iterative builds. So configuration of whether or not you're using Unity builds could be useful here. Depends on the Unity build group size. Clean build will benefit the most when you have nothing cached, just building from scratch a Unity build because you have to build everything. Similarly to pre-compiled headers, you can break your build. So exactly the same reason, if you are sloppy with your includes for whatever reason, because everything's being included together, the include that you rely on will be there. But then if you try and build under a regular configuration, you might be missing an include, so you could break everything. So for that, just regularly build under a standard configuration on a CI job, just to ensure that you're building under no Unity build assumptions. Number of one-to ODR issues and other building compatibilities, so you're going to have to make some changes if your code base was not originally written with Unity build in mind. And if for whatever reason you can't do Unity build for your project, I just recommend trying to reduce the number of files, because merging smaller files together means less parsing of all of your includes, and so you're getting that additional benefit that Unity gives you. A lot of small files kind of eats into that. So, the main takeaways. As Jeff mentioned, first thing, just profile your build, determine what is taking up the most time and focus on that first. So that's what we did with forward declarations, removing unused includes and splitting protocol implementation. Those 3 together gave us a 60% reduction in build time. Look at merging your executables. If you have common code, that gave us a 10% reduction. Pre-compiled headers, very easy. I recommend you try it out. 20% reduction for us. That really does depend on your project. And then Unity build got us down to 50% with that one caveat of potentially changing your underlying behavior without realizing. That, I think, is everything we have for you. So it just requires us to give a shout out to one of our teammates, Dallas Clement, who couldn't be here today, but also really helped in this project, and the rest of our team who all contributed throughout the hackathons. Thank you. Thank you. Oh, the microphone's broken. That's okay. No questions.
This time I'm going to put myself the first in the queue.
Okay.
So I have a comment and a question.
Okay.
So the comment is a side comment when you mention the so-called fundamental theorem of software engineering. So I have to make 2 corrections. The first, the quote was incomplete, because it's every problem in software engineering can be solved with an extra level of indirection, except the problem of too many levels of indirection. The quote is not from Andrew Koenig. This was first stated by David Wheeler, who was the PhD advisor of Bjarne Stroustrup, and was also the first person in the world in getting a PhD in computer science at University of Cambridge.
Thank you.
So, I mean, I've seen this quote to many people, not only under Koenig. So every time I have the opportunity to fix, I have to do it.
Yeah, fair enough. Fair enough.
And I got the quote for a reliable source, who is Viernes Tuesday. Okay, now I assume that you didn't have any slowdown in your executable. Is that right, or almost right?
Almost right.
I knew that.
It is the trade-off you pay. Is that, yeah, you do get the additional layer of indirection can cause a slight slowdown. We did not determine it to be material for our use case, so it was acceptable for us because it really wasn't that noticeable for what we were doing. But in high performance computing, I know in other teams, they have made that comment. It's just like, we do notice an impact. So it really depends on the use case.
Yeah, because for example, your protocol implementation means extra memory allocation, yes, and that has an impact. And now my real question is, did you consider to move into C++ 20 modules? Because I think some of the problems here could also be perhaps solved by C++ 20 modules.
So I think you might have missed my first slide on C++ modules.
I had to get outside for 1 second. I'm sorry.
So that's totally fine. I did try to preempt that question up front. But yes, C++ 20 modules should solve this question, should solve this problem for us. It looks very promising, but the issue we have is all of our third-party dependencies are not yet on modules.
Yeah, sure.
And it's going to take a while for us to transition. So this is what we did in the meantime.
And apologies for not being there for 1 minute. So now, Peter.
My question is, Unity build, you wouldn't have to use impl at all, because, so the question is, did you undo those changes again?
We didn't undo those changes because mainly for testing purposes and separation of dependencies, we found it useful for the test frameworks. So we kind of appreciated that. So we haven't undone that change. But yeah, I fully agree. That problem does go away with Unity build.
I see lots of hands. I like that.
I have two questions. Which linker do you use? And the second is the Google guideline about the forward directions. The last time I looked at it, many years ago, I read that Google says do not use forward declarations because the class you forward declare could be a base class or derived from somewhere, and this is not seen if you just have a forward declaration, and then you may call different functions before and after the compiler sees the whole definition of the class.
Okay, yeah, so the first question was on linker. We were using LLD and then we switched to mold. We had a few issues with mold, which then since got resolved. So I can now vouch for mold, significant performance increase. On the forward declarations, yes, there are potential issues. I'll discuss further with you the one on the base classes, because I was aware, but we can discuss further. For us, it's very much the approach of use it when you have awareness, don't use it blindly. And that's kind of the approach we took, is that only forward declare what you own that you have knowledge of, because otherwise, yeah, you can run into issues. Okay.
How much was the decrease, the speed up when you used mold?
I think I'd have to double check. There is some profiling actually on the mold site, on the mold website compared to LLD, and I think twice as fast on the linking side, but I don't have the specs off the top of my hand. So.
Okay, so my question is regarding C++ models. So you talk about adopting C++ models and that. So do you have like a time frame, or have you defined in your roadmap a moment for using the models, for adopting it? Have you been doing some first approaches, some tries? How are you managing right now the models? If you can disclose your results.
So I think my official statement is I can't disclose that. But generally speaking, Bloomberg is a 40-year-old tech company. So there's a lot of code that exists, and that is the real challenge, is the code that exists, migrating it. For new projects, obviously it's much less of a problem. You can definitely work with it a bit more. But on the older projects, It's on our roadmap. I can't say any more than that.
Okay, thanks anyway.
Hi. So I have one question, and it has to do with how do you prevent regressions to the compile time?
Okay, yeah. So what we actually have is on our CI job, we output all of the timings. So we save that. We have a little script to basically keep track of that. And so we can monitor that over time. We have a dashboard, just keep track of it because you have all of that data for your CI pipeline. And so we monitor that on an ad hoc basis, reassess type thing. We haven't actually put in alarming, but it's very noticeable. Like if you're compiling locally and you suddenly notice that something's taking a bit longer, it's like, have we changed anything? We can go back and check the history of our CI pipeline to see if there's spikes for anything. So just keeping an eye on it.
Thank you. I had one question. Without taking into account, for example, the Unity build, it doesn't show, for example, if you use normal header guards like ifdefs or pragma ones. Do you think there will be any difference in terms of the speed if you use one alternative or the other, or none in this case?
Between pragma once and ifdef? Yes. Okay, I'm not an expert on this, but my understanding is that my understanding is that there's a negligible difference these days. Is that wrong?
I think I know what Nico is about to say.
No.
Comment or a question?
No, it's a question. I'm polite.
Then a comment. Pragma once is not standard C++.
Yeah, there you go.
Well, there are other things than standard C++ that work. So my question is, modules, did you already look at it a little bit, whether you could see profiling and see some benefits on the horizon? So
on the module side of things, I've seen open source people looking into it and trying to profile it and saying this is significantly better. On our scale, it is a little bit prohibitive to actually try and get that profiling because we have so many dependencies. So there's very few things that are modularized that we can use, and that's our drawback.
Any other question? Then Peter.
Okay, I have one more question about your source code preparation, especially for the first level where you did the include what you use things and the forward declarations. Can you give an estimate how much effort, manual effort or human effort went into that?
So the include what you use is some open source tooling. So we actually did our own variant of that. We kind of experimented with Clang query to try and figure that out and had moderate success. Then for the forward declarations, the first thing there was actually via the Clang ftime trace and determining which headers were included, because Clang's ftime trace, if you aggregate over the results, it tells you how many times every header was included. And that was actually where we found label translator. It was included 500 times. It should not be included that much throughout the code base. And so that one we couldn't actually forward declare. But it's in cases like that to get an insight, what are your dependencies and what shouldn't be a dependency.
Just to let you know, well, it's extinct now, the project, but we had tooling, interactive tooling for Eclipse that did include optimizations and refactorings towards forward declarations.
Okay, that's interesting. Do you know why it's...
nobody was eager to pay for something like that.
Okay, thank you.
And I left the university.
Thank you.
There is something that is not going to solve problems, but because macros are evil. But please, if you have an enum type, your enumerators should not be all capital letters. All capital letters is just for macros, not for constants, not for enumerators.
I'll tell my third-party provider.
Third parties are a problem. Yeah, I said this is not going to solve anything, but I wanted to make the comment. More questions? More questions too?
We still have time. You mentioned that you moved from multiple test executables towards using libraries. Many unit testing frameworks use static initialization for test self-registration, like Catch, for example, that we've seen today. And in the 90s, we had the problem with those things when we put test cases and other stuff that also used static initialization into DLLs or even libraries, that the cross-file or cross-translation unit dependencies were not resolved properly, and we had things like programs crashing before even main started because of the static initialization order fiasco. Did you ever encounter that, or did you do any countermeasures to prevent that?
I have to admit, we didn't encounter that, but I can definitely see the problem. I guess in our case, we were lucky we didn't hit that.
So you were just lucky.
Sometimes you need a little bit of luck.
Okay. Now I ask again, any other question? Okay, thank you very much.